Hi all, Semiconductors MCQ Set 1. Let's start the video. First question, which of the following correctly compares conductors, semiconductors and insulators based on their energy gap? Option A, conductors have the largest gap, insulators have the smallest. Option B, semiconductors have the largest band gap, conductors have the smallest. Option C, insulators have a large band gap, semiconductors have a moderate band gap, conductors have no band gap. Option D, all the three have the same band gap. This first question is based on the band gap, energy band gap of conductors, semiconductors and insulators. Energy band diagram of insulator, semiconductor and conductor. This is the valence band and this is the conduction band and they are separated by a band gap. In the case of insulator, the band gap energy Eg will be greater than or equal to 5 electron volt. In the case of semiconductors, this valence band and the conduction band, they will be separated by an energy gap Eg which is approximately equal to 1 electron volt. In the case of conductors, both the valence band and the conduction band will be in the overlapped position. So from this figure, we can understand that the band gap energy or the band gap separation between the valence band and the conduction band is highest for insulator, then it will be semiconductor and then it will be conductor. We can see that the insulators have the largest band gap, semiconductors are having the moderate band gap and conductors are having no band gap. So the answer is option C. Some comparison between the conductors, semiconductors and insulators. A conductor can conduct electrical current easily. In the case of semiconductors, the current conduction will be more than that of insulator but will be less than that of conductor. In the case of insulator, an insulator does not conduct any current. So this is the conductivity. Comparison between conductor, semiconductor and the insulator. Next one is the valence electrons. In the case of conductor, it will be having 1 valence electron. In the case of semiconductors, it will be having 4 valence electrons. And in the case of insulators, it will be having 8 valence electrons. That is, it will complete the octet. Next, the bond. In the case of conductors, it will be having the metallic bond. In semiconductors, it will be having covalent bond. And in the case of insulators, it will be having the ionic bond. Next is the energy gap. We already seen the band gap figure. In the case of conductors, the valence band and conduction band will be in the overlapped position. In the case of semiconductors, the energy gap will be approximately equal to 1 electron volt. And in the case of insulators, the Eg will be higher than or equal to 5 electron volt. Now, in the case of resistance, the conductors will be having very small resistance. Semiconductors will be higher than that of conductors and insulators, the resistivity will be very high. Now, very important one point is temperature coefficient. In the case of conductors, they will be having the positive temperature coefficient of resistance. In the case of semiconductors, they will be having the negative temperature coefficient of resistance, and insulators also they will be having the negative temperature coefficient of resistance. So in usually the MCQs, this will be an important question, that is the temperature coefficient of resistance of semiconductor, it will be negative. And also sometimes they will be asking the number of valence electrons in the case of semiconductors, that will be equal to 4 electron volt. Also some cases they are mostly asking this question, that is the energy gap in the case of semiconductors, that is approximately equal to 1 electron volt. Okay, this is an important chart. Next question. Intrinsic semiconductor is one which option A contains only acceptor impurities, option B contains only donor impurities, option C is perfect pure without any impurities, option D has equal number of donors. And before going to the answer of that question, we can see the semiconductor materials, they are usually classified into 2 types, that is intrinsic semiconductor and extrinsic semiconductor. An intrinsic semiconductor is one in which it is in the pure form. They are called the intrinsic semiconductor. To get the extrinsic semiconductor, we are adding a impurity to the intrinsic semiconductor. The process of adding the impurity to the intrinsic semiconductor is known as doping. Okay. Doping, by adding the doping or the impurities to the intrinsic semiconductor, the conductivity of this intrinsic semiconductor can be increased. That process is known as doping. Then that semiconductor after doping, it is known as extrinsic semiconductor. There are two types of doping usually, that is by adding the n-type impurity and also by adding the p-type impurity. By adding n-type impurity means the impurity atoms which are having 5 electrons in its valence band, that is pentavalent impurity. Next one, the p-type means by adding the atoms which are having 3 electrons in its valence band, that is the trivalent impurity. Now, the n-type semiconductor can be obtained by adding phosphorus, arsenic, antimony, then bismuth, etc. That is, this is the n-type impurities. This is very important. We have to know which are the impurity, n-type impurity atoms. That these atoms are also known as donor type impurity, because they are giving or donating 1 electron. So, they are known as the donor type impurity. Now, the p-type semiconductor can be obtained by adding aluminium, indium, gallium, boron, etc. So, this are known as the trivalent impurity. And also, this p-type impurities are also known as acceptor impurities or acceptor type impurities. Okay, this is the basics of what? Semiconductor materials. Now we can go to the answer of the previous question. We can go to the answer. The intrinsic semiconductor is one in which is perfectly pure without any impurities. The answer is option C. Next we can move on to the next question. An intrinsic semiconductor, the number of electrons is option A greater than holes, less than holes, option C equal to holes, option D 0. In the case of an intrinsic semiconductor, the number of electrons will be equal to the number of holes. So, we can write the number of electrons is equal to the holes. That is option C. That is, number of electrons will be equal to number of holes in the case of an intrinsic semiconductor. Next question. Adding pentavalent impurity to silicon creates option A intrinsic semiconductor, option B p-type semiconductor, option C n-type semiconductor, option D insulator. We had already discussed in the case of, if we are adding pentavalent impurities means they are n-type impurities. Okay, if we are adding the n-type or the pentavalent impurities, the silicon, it will create what type of semiconductor? It is an n-type semiconductor. So, the answer is option C. Next one. Which of the following is a trivalent impurity? For option A phosphorus, option B arsenic, option C boron, option D antimony. Trivalent means this is which material? P-type, right? P-type. What are the P-type impurity atoms we are usually using? Boron, gallium, indium, like that. So, from this we can see that the trivalent or the p-type impurity here is boron. That is option C. The majority charge carriers in a p-type semiconductor are option A electrons, option B holes, option C both equal, option D depends on the temperature. In the case of p-type semiconductors, the majority charge carriers are holes. Answer is option B. Next question. Donor impurities create energy levels. Option A close to the valence band, option B close to the conduction band, option C at the mid gap, option D above the. See the figure. In this we can see that this is an intrinsic semiconductor. This is the conduction band and this is the valence band. In the case of an intrinsic semiconductor, the Fermi level will be in the middle of conduction band and the valence band. In the case of an n-type semiconductor, the donor level and also the Fermi level will be just below the conduction band. That is, then in the case of p-type semiconductor, the Fermi level will be above the valence band. So, this is an important figure. So, in the case of an intrinsic semiconductor, the Fermi level will be in the middle of conduction band and valence band. In the case of an n-type semiconductor, the Fermi level will be below the conduction band, and in the case of p-type semiconductor, the Fermi level will be just above the valence band. Now, what will be the effect of temperature? In the case if the temperature is above 0 Kelvin, in the case of an N-type semiconductor, the Fermi level will drop with the increase of temperature. That is, the Fermi level will move downwards. Okay. In the case of P-type semiconductor, with the increase in temperature, this Fermi level will move like this, the upwards. So, this is the trend with the increase in temperature. Question: donor impurities create the energy level. Option A, close to the valence band. Option B, close to the conduction band. Donor type impurity means N type, right? In the case of an N type, the energy level or the Fermi level will be close to the conduction band. So, answer is option B. Now, acceptor impurities will create an energy level. The acceptor level will be just above the valence band. So, the answer option A, just above the valence band. Option B, just below the valence band. Option C, near the conduction band. Option D, at the band gap center. The answer is just above the valence band. Next question: which of the following is not an extrinsic semiconductor? Option A, silicon which is doped with the boron. Option B, silicon doped with the phosphorus. Option C, pure germanium. Option D, germanium with the arsenic. We know that these three cases they are doped, right? The first silicon is doped with the boron. Then second case, silicon is doped with the phosphorus. And option D is germanium with the arsenic. So the answer is the which is they are asking for, which is not an extrinsic semiconductor. So which is in the pure form, that is the intrinsic semiconductor. The process of adding impurity to pure semiconductor is known as option A, ionization. Option B, doping. Option C, amplification. Option D, saturation. The answer is option B, doping. Conductivity of a semiconductor increases with option A, decrease in temperature. Option B, increase in temperature. Option C, independent of temperature. Option D, crystal structure change. In the case of an intrinsic semiconductor, the conductivity will increase with the temperature. The answer is option B. Which material is commonly used for P-type doping? Option A, phosphorus. Option B, arsenic. Option C, antimony. Option D, boron. Here they are asking for P-type. P-type impurity here is which one? Boron. So the boron is a trivalent acceptor impurity to create a P-type silicon. So the answer is boron. Option D. What happens to minority carrier concentration when the doping level increases in an extrinsic semiconductor? Option A, increases. Option B, decreases. Option C, remains constant. Option D, becomes 0. Due to the heavy doping increases, the majority charge carriers will increase and it will suppress the minority carriers according to the mass action law. So the answer is option B, that is it decrease. Band gap of intrinsic silicon at room temperature is approximately option A, 0.3 electron volt. Option B, 0.7 electron volt. Option C, 1.1 electron volt. Option D, 2.1 electron volt. So in the case of an intrinsic silicon at room temperature, the band gap is 1.1 electron volt. Answer is option C. Next one, an N-type semiconductor has option A, more holes than electrons. Option B, more electrons than holes. Option C, only holes. Option D, only electrons. In the case of N-type semiconductor, we are adding what type of impurity? Donor type of impurity. So they will add more electrons. So in the case of an N-type semiconductor, there will be more electrons than holes. The answer is option B. Next question. In a P-type semiconductor, the minority carriers are option A, electrons. Option B, holes. Option C, both equal. Option D, none. We know that in the case of P-type semiconductor, the majority carriers are what? Majority carriers are P-type case, the majority carriers are holes and minority are electrons. So the answer is option A. The minority charge carriers are electrons. I hope you understand the video. Thanks for watching. Please do like, share and subscribe. We can discuss more questions on the coming